you're at a 30% increased risk of accidents and injuries when you drive under severe low visibility conditions. But what if your car could talk to other cars and see what they're seeing? Would that lower your chance of hitting someone or being hit? You might be thinking, yes, it would help. But what if other cars also had equally bad visibility? Tesla uses a single giant neural network known as transformer, receiving inputs from 8 cameras at a time, but essentially, all those cameras are mounted on one car. What would be the likelihood of accidents if self-driving cars could talk to each other? That's what we're talking about today. What's up everybody, welcome back to the channel. Sadia here. I'm an electrical engineer doing Ph.D. in machine learning, and on this channel I usually talk about engineering, machine learning, and some scholarships in our field. So if that's something that interests you, you might want to subscribe to the channel. Alright, so Tesla uses neural networks to train their self-driving cars. More specifically, they use convolutional neural networks. Convolutional neural networks require a large amount of data to be trained. Tesla uses data from third parties as well as data that's collected by their own cars, and then they have a team of engineers who label this data. Later, Tesla uses this labeled data in combination with other unlabeled data that is automatically categorized by other machine learning systems to train their self-driving cars. Tesla even dropped radars from one of their more recent models because they are relying more and more on Tesla Vision, which is a camera-centric autopilot system. So, would a camera-centric autopilot system benefit from talking to other cars in the vicinity? That's what I want to talk to you about today. The idea stemmed from one of my most recently published papers. It's called Partially Cooperative Scalable Spectrum Sensing in Cognitive Radio Networks Under SDF Attacks, and it is published in IEEE Internet of Things journal. You can find it by searching for my name on Google Scholar or IEEE Explore, but if you want to read the paper, I will also link it in the video description. The idea is ridiculously simple, and I actually used the analogy of reserved traffic lanes to explain the concept in a previous video. And it was actually the use of that analogy that got me thinking, wow, the same idea applies to self-driving cars. Imagine you're driving in extremely low visibility conditions, so you have about 20% chance of a false imagery. There is, let's say, a bike, an object, and you have a 20% chance of either missing it or thinking that there is one when there's nothing. So you basically have a 20% chance of a wrong judgment. Could this risk be reduced if your car could talk to other cars in the vicinity? Now, do keep in mind that the other cars also have the same low visibility. They also have a 20% chance of hitting an object by making an incorrect judgment about its presence there. So, would the odds of you or the other cars hitting it change if your car could talk to the other cars? The idea is ridiculously simple, because if your car can talk to other cars and the chances of all 3 or 5 or 7 cars making an incorrect judgment at the same time are very, very low. I used the idea in my paper for spectrum opportunity detection. It's called cognitive radio networks, and basically when primary users are not using their spectrum, the secondary users can access the spectrum, but they have to accurately detect the presence of primary users. So they have certain chance of missing this object when it's there, just like a bicycle, and your car has a chance of missing it due to the poor visibility. In my paper, I used this very simple idea of a majority voting to improve the detection of a primary user in the spectrum when it's there. And the same idea applies to self-driving cars. Every car has a 20% chance of a false detection, basically thinking that an object is there when it's not, or thinking an object is not there when it is actually there. In technical terms, we usually call this false alarm and misdetection. On the horizontal axis, you can see the probability of individual cars making an incorrect decision, and on the vertical axis, you can see these probabilities after a majority vote. And as you can see, the probability after the majority vote is significantly lower for each level of individual incorrect decision making. The different colors in the graph actually represent a coalition size, which in the cars example represents the number of cars participating in this decision-making process or in this majority vote process. Large number of cars would improve the detection more, but as little as 3 cars can help increase the chances of less and less accidents. Let's say there are only 3 cars. One of the cars incorrectly classifies that there is no object, the lane is free, there's nothing, and I can just pass straight ahead, versus 2 other cars accurately detect that there is in fact a bicyclist right in front of you and you have a risk of hitting it. After the majority vote, those 2 cars' decision would overpower the individual cars, and all 3 cars would actually prevent your car hitting into that poor bicyclist. It is a very simple but very effective idea that I used in my paper. My paper is about the application of reinforcement learning to spectrum sensing in cognitive radio networks. So basically, I applied this on the mutual decision-making system when all the secondary users are detecting the PU's spectrum at the same time, they are looking at the same thing, and they have a 20% chance of incorrect decision-making. In my paper, I analyzed different levels of probability because they have to model different physical phenomena, to model different inaccuracies in the sensing process, and to model the SDF attacks on the network in which a malicious user is actually actively trying to mislead them to cause more accidents. And you can see how powerful this idea is. Individually, they have a much higher risk of accidentally hitting a PU, just like in the car example, a car hitting a bicyclist because of the incorrect judgment. But if the cars can talk to each other, they have a much lower risk of still hitting the bicyclist. I used majority vote to improve the reliability of spectrum sensing, and the same idea can be applied to self-driving cars. I'm sure whatever your field is, you can probably think of 1 or 2 ideas in which majority vote can help more accurate detection. Off the top of my head, I can think of dental x-rays or some medical tests, medical exams that require some accurate detection of certain things in those tests. What your field is and how you can apply the idea of majority vote in your particular field. Let me know in the comments. If you would like to get in touch with me, the easiest way would be on Twitter. You can just follow me at Sadia Khaf, or you can tag me in your posts. I always try to reply to all the posts I'm tagged in. So if you want to have a conversation about machine learning, the idea of majority vote, the concepts in reinforcement learning, you can always just tag me on Twitter and I will try to have a discussion with you on Twitter about it. The other way to get in touch with me would be through my newsletter. You can sign up for my newsletter, and in the reply to my newsletter emails, you can ask me any questions that you might have. I promise I don't sell any ads in the newspaper, only my genuine thoughts, only my machine learning related subjects or my grad school related subjects. Never ever any ads. I hope you learned something from this video. If you did, give it a thumbs up, subscribe to my channel, and if you would like to learn more about how I'm applying reinforcement learning, a branch of machine learning, in cognitive radio networks in a very simple and easy to understand way, I will link a video here in which I explain using a traffic analogy. See you next time.